Organic chemistry is the study of carbon-based compounds. It's unique for its 4 valence electrons, so it forms 4 covalent bonds. That gives it the ability to create long chains and complex structures. These structures have functional groups, recognizable patterns of atoms that determine a molecule's reactivity. Like alcohols contain a OH group. Carboxylic acids have a carbon double bonded to an oxygen and a single double bond to an OH group. Amines have nitrogen. These are the simple building blocks of biomolecules, things like sugars, fats, and amino acids. Then we get to reactivity. We often refer to mechanisms, step-by-step explanations of how reactions proceed. You take nucleophilic substitutions, for example. There's 2 classic examples of that, SN1 and SN2. In SN2, the nucleophile attacks the electrophilic carbon atom at the same time as the leaving group leaves. It's a single, concerted step, very elegant, resulting in the inversion of configuration, kind of like an umbrella going inside out. SN1, on the other hand, it's a 2-step mechanism. The leaving group has to go first, and then the carbon cation forms. Depending on stability, it determines the rate of reaction. Then the nucleophile attacks a positively charged carbon. The rate of an SN1 reaction is depending on the substrate, not the nucleophile. So polar protic solvent stabilizes the carbocation through solvation to keep it stable. That's why SN1 prefers tertiary carbons, because that's when the carbon is the most independent and stable all by itself. But in the SN2, steric hindrance becomes the most important limiting factor. Primary alkyl halides are ideal in polar aprotic solvents like acetone or DMSO increases the nucleophilicity without solvating the nucleophile, because it's important because like dissolves like with the protic and aprotic solvents. Instead of substitution where a leaving group leaves and a nucleophile replaces it, in elimination, leaving group gets eliminated. So in elimination to eliminations reaction, you will get an anti-periplanar geometry between the beta hydrogen and the leaving group to get the proper orbital overlap. But in the
E1 elimination reactions, the carbocation stability dominates, similar to the substitution 1 reaction. Resonance delocalization of electrons increases the availability of conjugated intermediates, especially in allylic or benzylic systems. That's why the reactivity of alkyl chlorides is higher than esters, because of lower resonance stabilization and the better leaving group's ability. The more unstable, the more reactive.
We also see hyperconjugation in tertiary carbocations where the single carbon-hydrogen orbital overlap with the empty p orbital to delocalize and spread off the charge. Don't forget about Hammond's postulate, of course. The transition state resembles intermediate, and if that is the case, then the endothermic steps will
favor the later transition states. For Linner's catalyst gives us
alkanes, but when you do sulfur metal reduction in liquid ammonia, we get the transconfiguration for alkane hydrogenation, obviously. And the conjugated dienes undergo 1,2 and 1,4 addition via an allylic carbocation intermediate, depending on kinetic versus thermodynamic control. Read by Markovnikov.